Okay, Bismillahirrahmanirrahim. So in this video I would like to walk you down through example 8.4, which is on a separately excited DC motor. Okay. Let me first read out the question. The motor in example 9.3 or 8.3, which is has been discussed on the previous video, is now connected separately excited as shown in the figure, and the motor is initially running with VA, the armature voltage, equals to 250 volts, armature current IA 120 amps, and the speed is 1103 rpm, while supplying a constant torque load. So in this question, the torque load is constant, and the question is, what will the speed of this motor be if the armature voltage is reduced to 200 volt? Okay, so to answer this question, basically we've got two states. We have two states. This one here. So we've got two states. Yeah. So the first one is when the VA equals to 250 volts, and the second one when VA is equals to 200 volt. Okay. Okay, and then in the question we've been told that IL is equals to 120 amps. Yeah. And then if you look at this equivalent circuit, IL is actually in this case equal to IA, or the armature current. So the line current is the same as the armature current. So IA is the one here. IA1 is equals to IL1, which is equals to 120 amps. Okay. Right. And then the question tells us that the torque or the load is constant. Yeah? Load is constant, which means that the torque of the motor is also constant. So theta 1 or torque 1 is equals to tau 2. Okay, from the questions we know that the load torque is constant. Yeah. So load is constant. Okay, because the load is constant, the motor's torque is also constant, which means that tau 1 is equals to tau 2. Yeah. And tau is equals to K prime time flux times, sorry, not N but IA, armature current, and this is also equals to K prime flux 2 times IA2. Yeah. However, because we haven't changed any parameters in the field circuit, yeah, the one that generates the magnetic field, yeah, this field here, this circuit here, because we haven't changed anything in there, so it means that the flux in the system is constant, and therefore the flux in the system is constant, and therefore theta 1 is equal to theta 2. Okay, and then we can simply write it as theta, and therefore we can then change this into K prime flux IA2. Okay, and then we can cross this out. These two are the same, and the flux also the same, and therefore we can conclude that IA1 is equals to IA2. Yeah, so there is no change in the armature current, and therefore then we can write it down here that, I've written it down before because of the mistake I made previously. So IA2 is equals to IA1, which is equals to 120 amps. So we know that the EA is directly proportional to the speed, so we can write down the ratio of EA, which is EA2 over EA1, is equal to the ratio of the speed, which is N2 over N1. Now we want to solve for N2. We know already N1, so to solve this equation we need to find the values of EA2 and EA1. Yeah? And by using KVL, looking at or referring to the equivalence circuit, EA plus the voltage across RA will be equal to VA, the armature voltage. So we can write down that EA1 plus IARA, which is the voltage across RA, is equal to VA1. And similarly, for the second state, we can write down that EA2 plus IARA, which is IA2, equals to VA2. Now if we rearrange to solve for EA, EA1 is equals to VA1 minus IA1 RA. Then we can substitute the variables with the values. 250 minus 120 times 0.03, and this should give us 246.4 volt. And similarly for EA2, we can work it out, is equal to VA2 minus IARA, specifically IA2 here, which is equals to 200 minus 120 times 0.03, which is 196.4 volts. So now we've got all the values of the variables that we need, and now we can solve or find the value of this new speed N2, by using the equation, the ratios. So N2 is equal to EA2 over EA1 times N1. Then we can fit the values. 196.4 over 246.4 times 1103, and this gives us 879 RPM for the new speed. Thank you.